Thank you very much and good evening. So the last presentation of the session. I will be talking about comparing the efficiency of various post-processing methods on the structural integrity of laser powder bed fusion samples. This is a collaboration between University of Politico di Milano and NTNU in Norway. So additive manufactured samples are generally characterized by a very irregular surface morphology that is affected both by the technology that is being used for fabrication of the samples and also the parameters that are implemented in each technology. In this image, you can see three different technologies, and within each technology, the parameters like the size of the powder or the energy input or the laser powder power is changing, and that is changing a lot the quality of the surface. There is another issue because we are always bragging about the capability of additive manufacturing for obtaining very complex geometries, but that is coming at an increased cost. The fact that we will have, depending on the direction of the surface with respect to the build direction, we will have very wide range of, let's say, variation between the surface quality at different areas of the geometry with a, let's say, complex shape. So in this study, we have been trying to design different post-treatment methods in order to address and alleviate, let's say, these adverse effects of surface roughness and high surface irregularity in laser powder bed fusion technology. We selected a notched geometry in order to have this down skin and up skin difference also in terms of surface quality. The surface treatment, the term treatments, let's say post-treatments that we have considered include heat treatment, surface severe plastic deformation treatment, chemical surface treatment, and also hybrid treatment, so combinations of severe plastic deformation and chemical treatment. Here you can see an overview of the treatments that have been used, including T6 heat treatment, chemical polishing, electrochemical polishing, shot pinning, ultrasonic nanocrystalline surface modification, severe vibratory pinning, and laser shock pinning. So we have been applying each of these treatments individually and also their combination with the heat treatment. The mechanical surface treatments, including also, if I include also the laser shock pinning, are supposed to do not remove any material, but they are just regulating the surface softness due to the severe plastic deformation. They are also inducing compressive residual stresses. They can cause surface grain refinement and gradual change of the hardness of the in the material towards the core. In some cases, as I'm showing you in the next slides, we have been able also to close the pores that are very close to the surface with these severe plastic deformations. On the other hand, the chemical methods are just removing a very thin layer of material from the surface in order to smoothen the surface roughness, and they are not interfering with the bulk material properties. Very briefly, just to show you the results of the heat treatment that was applied on half of the samples, is that we are starting from a very irregular surface, irregular structure in terms of the microstructure of the samples, depending on the build direction and the section that we consider with respect to the build direction. And we have, after the heat treatment, this laser tracks are completely fading. The distribution of SI particles in the aluminum matrix is becoming much more regular. So we are let's say, somehow eliminating the anisotropy in terms of microstructure that we have with the applied heat treatments. Interestingly, the mechanical surface treatment resulted in a structural and also chemical gradient in our structure. So structural in terms of grain refinement on the surface, and was gradually increasing as we are going to the core of the material. And also in terms of the chemical gradient, we have the density and size of the SI particles that are closer to the surface as we go towards the core material. And these results were affecting the distribution of the hardness and also residual stresses depending on the kinetic energy of the treatment. Here I'm showing just the main parameters in terms of surface microhardness, in terms of surface residual stresses, depth of residual stress, and maximum residual stresses that were changing depending on the treatment that was applied on our material. In terms of porosity, again, in some cases, the treatments, especially the severe plastic deformation based ones, were able to reduce the overall porosity by closing the subsurface porosity, especially the laser shock peening was very efficient in reducing, in closing the subsurface porosity and reducing the overall porosity. Here you can see the morphology of our samples, what I was talking about, again, the irregularities having a very high density of partially melted powder spatters and or agglomerates on the down skin, on the notch area, and that which was having the highest surface softness in the notch area, followed by the notch root and then the upper skin. The treatments were able to reduce considerably the surface softness. So depending on the treatment, of course, the chemical treatments are much more efficient in smoothing the surface, but even shot peening, although it is not known as a treatment to reduce surface softness, it was reducing the surface softness considerably compared to the as-built case, because it was eliminating these partially, let's say, melted powders that were randomly distributed on the surface. And then finally, the fatigue test. What we, apart from the, let's say, the improvement in the fatigue life of the samples that I'm showing in the next slide, what was interesting is that we expected the fatigue fracture to happen from the notch root that is supposed to be the most critical section, but because of these irregularities that we have on the down skin of the notch area, in most cases in the as-built and also heat-treated samples, the fracture was always happening on the down skin, and the treatments, the post-treatments were able to displace the fracture surface and get it back to the most critical area. So they were eliminating the effect of the irregularities on the down surface, on the down face, and then bringing it back to the, let's say, critical area that should be the notch root. Here you can see these, let's say, the position of the fracture surface that has been quantified with this relative height in notch parameters. And as you can see, for the as-built and the heat-treated samples, they are much higher with compared to the notch root, and they are getting much closer to this 0.1, 0.5 value that is the position of the notch root. And then in terms of the fatigue life, again, we have a considerable fatigue life improvement or rotating bending fatigue tests that were performed after the post-treatment. Just to conclude here, I'm showing the fact that there are a large, let's say, range of parameters that can be modulated by post-treatment in terms of the microstructure, in terms of hardness, fatigue, wear, corrosion, and the, let's say, different functionalities of the samples. And depending on the geometry of the sample, the cost and the type of the material and the target application, these post-treatments should be tuned in order to get the best results. Before concluding, I just want to invite everyone, the audience online and here, to participate in this 14th International Conference in Shot Peening that we are organizing in Politecnico di Milano in Italy in September. It's not including just shot peening, but all impact-based surface treatments. So everyone would be welcome to participate to the conference. Thank you very much.